Right now. Okay. Um, Today is Monday the 10th. Um, your quizzes and activities are going to be up later tonight. Sorry for the delay. Um, so those will be up. Then we have lecture today. We have new material on Wednesday, the 12th. And then a week from today, we will be reviewing for our exam, which is going to be on Wednesday, the 19th. So, all of that to say, I wanted to go ahead and get started, and I wanted to share some poll questions. And these poll questions are a little bit of I think that they're good questions, really affirming um, a couple of the different things. For instance, a Km, and that's one important thing. So a double reciprocal plot has the y-axis label of 1 over Vmax, Vmax, substrate concentration, 1 over substrate concentration, and 1 over V sub 0. So this is a subtle thing, but whenever you see this, when you see this sort of question, one of the things that it's important to be cautious of is this says the y-axis label. So when we think about a double reciprocal plot, the actual label for the y-axis is 1 over initial velocity. Now, when it comes to the y-axis, and one of the other things that we're pretty interested with respect to the y-axis is we are interested in the intercept. The y-intercept is is going to be 1 over Vmax. So when we have our data plotted, that y-intercept is our 1 over Vmax. So this question in particular is asking about the y-axis label, and that is just this right here. So the correct answer for that was 1 over initial velocity. Now, I just want you to have that question kind of in your repertoire because I've asked that sort of question before, and I don't want you to fall into the trap of not trap, but I don't want you to, you know, walk down that path and feel good about it, and then end up with that as your incorrect answer. Okay, so now I've got two questions kind of packaged together. The first question reads, imagine an enzyme with two potential substrates. So the enzyme catalyzes two reactions. One reaction is it takes, well, reactant A and converts it to product C. This enzyme also gets reactant B and converts it to C. Okay, this enzyme's Km for A is 0.1 millimolar. So Km, I'm going to label that A, is 0.1 millimolar. And then B, Km B is 0.1 nanomolar. Which Km is lower, A or B? Okay, so we've got A, B, they're the same, nobody knows. And if you're looking at this and thinking to yourself, well, that's just a question of units, you're right. Okay, so then question number two is you have two separate reactions. The same amount of enzyme is in each reaction container or vessel or beaker. In beaker number one, I'm going to draw this. We got beaker number one and beaker number two. In beaker number one, you have 0.01 millimolar of A and none of B. And then in beaker number two, you have 0 of A and 0.01 millimolar of B. Which container has the enzyme in a solution with less substrate than its Km? So what I want you to be thinking about here is thinking about what the Km is. The Km is the substrate concentration that your enzyme needs to get to half of its maximum velocity. So it's a measurement. And so we have our Kms up here. Km for A is 0.1 millimolar, and Km for B is zero point 0.1 nanomolar. So which one of them has less than its Km? See something in the chat. Same Km for the first question. My, can you send me pull back? The pull. Okay, so can you send the pull back? I don't know how it's open, so I don't really know how to let me see if I can get a QR code. I can paste that. Nope, that's not it. Okay. Okay, so our Km, and I'm going to erase this over here. Sorry, I don't know how to reopen the poll for anyone. Okay. Okay, so can I repeat the definition for a Km? Absolutely. Our Km is the amount, or let me change that, is your substrate, and I'm going to bracket this, substrate concentration that gets your enzyme to Vmax divided by 2. Let me scroll back. So yes, I had a question I meant for are we using the same Km values from the first answer? Yes, we are. And if you answered one but didn't answer the other, don't worry about that. Okay, so what I've got right now is about 60 out of 68 people have answered. 61, okay. And then the second question, we're at 61 out of 60. Okay. Okay, so the response for question number 1. Now, just so you guys are all on the same page with this, 0.1, that's lowercase m, capital M, millimolar. Okay. Now for number 2, 0.1 nanomolar. If you haven't, or if you've maybe not used things on a micro scale, I think that it's helpful as biochemists to think about things in terms of micro scale, because if you've ever had the chance to use a mechanical pipetteman, a mechanical pipetteman basically has a range of up to 1,000 microliters, which is 1 milliliter. So I always like to think about in terms of units, like if you remember back to Gen Chem 1, you would talk about your metric prefixes. So you would go grams to milligrams, and then from milligrams on to micrograms, and then micrograms down to nanograms. So think about those prefixes. I think that's a really good place to think about. Now, when we look at these two, the question that was asked was basically which one of them is lower, which has a lower Km. And what I can show you is that, or what I can show in just a second, is that 78% of folks picked B. You are correct. Great job. Okay, so now my next question. I'm going to erase. Oh, no, that's my definition. I like to keep that one there. Okay, so now my next question is, which container has the enzyme in a solution with less substrate than its Km? Okay, so if we're to compare this, well, looking at beaker number 1. Beaker number 1, we've got 0.01 millimolar. 0.01 millimolar is less than 0.1 millimolar. Then we've got container number 2, or beaker number 2. That's 0.1 millimolar. And you might be thinking like, okay, I can't really remember milli to nano to pico or anything like that. Um, this a sorry, that should be lowercase m, capital M, and then B. Um, this quantity right here, 0.01 millimolar, is greater than 0.1 nanomolar. Okay, so that was just a kind of a refresher there. So I'm going to go ahead and stop the poll and I'm going to share the results. So from these two questions, most close to or the majority of y'all got B correct, and then we had a majority on A, or sorry, in question number two that were correct over the other answer options. Okay, so we're kind of going through a progression here of like, well, what's next? So we've got kind of an idea of what Km is. It is a substrate concentration, and it is the substrate concentration that gets you to half of your maximum velocity. So I know that I mentioned last time, and maybe this didn't stick, or maybe this didn't really attach, but I think about it almost like a compensation. You have to give your enzyme this much substrate in order for it to catalyze the reaction at half of its maximum velocity. Okay. And that's kind of our baseline important kinetic parameter as biochemists, Km and Vmax. Vmax, that's mostly self-explanatory for folks. Maximum velocity. Got it. Km is a measure of what is that substrate concentration. So now we've got another question popping up here. Oh, wait, a poll result. Oh, I gotta stop sharing that. Okay. Once I've stopped sharing that, then I can go on to launch. Interesting. I'll have to look at that, Brianna. I like that. Okay. So same situation. We have our two reactions. The same amount of enzyme is in each reaction container. In beaker number one, you have that 0.01 millimolar of substrate. None of B is present in beaker number one. In beaker number two, you have 0.01 millimolar of B, but none of substrate A. Which of the statements below is most accurate about the beakers? We're still using those KMs that we had from the first question, which I've left up there. We've got answer options. In both beakers, the enzyme is catalyzing the reaction at above Vmax over 2. In both beakers, the enzyme is catalyzing the reaction at below Vmax over 2. In both beakers, the enzyme is catalyzing the reaction at Vmax over 2. Then we've got one is above, one is below, one is above, one is at, and one is at and one is below. I know that that's a lot of different answer options. So the way that I think is helpful to think about this one is let's just go one by one. When we look at vessel number one, we have given our enzyme less substrate than its Km. We've given it 0.01 millimolar. So is it going to be able to catalyze the reaction at Vmax over 2? Nope, we're not giving it enough of its substrate, of its needed substrate. Okay, so that's a good indication that we've got one that is below. Okay, so that gives us a couple of options that we can dismiss. So I'm going to go ahead and write a note here. Enzyme below Vmax or V over 2. I'll just say, oh, darn it, Joel. Vmax over 2. Okay. Vessel number 2, we've got 0.01 millimolar of our substrate. So if this 0.1 nanomolar is our Km, then are we above our Km? For this one, yeah. This, sorry, this 0.01 millimolar of B, our other of our one of our other substrates, this is above our Km. Therefore, our enzyme is catalyzing the reaction above Vm over 2. Okay, so that leads us to, well, we've got one that's below Vmax over 2, and then one that's above Vmax over 2. Okay, now I'm going to go ahead and end the poll right there. Share the results. 73% of y'all answered, yeah, one was above, one was below. Now, I'm going to go back. I'd like to see response. Does that make sense? Okay. Okay. Two yeses, a couple of nods. Um, Now, what I think is important for thinking about KM is the poll did not pop up for you. Okay. If you're on the app, then I think that you might have to tap your screen. Or I'm not exactly sure what to say about that. So I'm not sure why. But what's very important to do when you think about your KM, we'll have a couple more poll questions, so I'd like to see if that happens again. Always think about your KM and remember that it is a substrate concentration, or it's kind of a demand that gets you to a, a rate. So if your substrate concentration is greater than your KM, what does that mean? That means you're greater than Vmax over 2. Now, one thing that people have a tendency to fall kind of into is they hear, oh, well, it's above Vmax. And then they pause and they think, wait a minute, above Vmax? That doesn't make any sense. Vmax is your maximum velocity, the maximum rate that the reaction could go. So how could, wait, remember, it's Vmax divided by 2. Those are the points that we correlate there. Okay, so what we are going to do today is I'll pause for any questions that folks have. Go ahead and ask them as I'm going to go ahead and move on to our next. So here's some of our learning objectives from last time. And what we're doing today is we're going to kind of populate the rest of our ideas and ultimately get to this slide right here, where we have all of our different plots, our inhibition plots, and you'll be able to look at that and identify which type of inhibition we're talking about. Just to clarify, is the maximum velocity for the enzyme or the reaction itself? The enzyme, because it's an enzyme catalyzed reaction. The enzyme is going to be driving that. That's a great question. Okay, so now um, if you that last slide is basically kind of where we're going and what I want everyone to kind of take away from this. Okay, so just to bring back the double reciprocal plot. This is what it is. Our important parts about it are our labels for our y-axis and our x-axis. And then I'm going to switch colors to highlight our intercepts. Our y-intercept is equal to 1 over Vmax. Our x-intercept is equal to negative 1 over Km. Your x-intercept is going to be a negative value. So if you get like negative 3, set that equal. Say negative 3 is equal to negative 1 over Km. And you will have questions where I could give you a plot and I'll have something like this. I'll have my axis labeled and I'll be like boom, 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 boom. I'll label it up here. Negative 1, negative 2, negative 3, negative 4.2. What is, or solve for Km, in which case you'd say negative 4.2 is equal to negative 1 over Km. And what we're doing with a Lineweaver-Burke plot is we are taking nonlinear data and we're plotting it to make it more linear. basically to make it more friendly so our approximations can be more accurate. Um, where we're what we're wanting to extract from this is we're wanting to extract our Km and our Vmax. Basically, how fast can an enzyme catalyze a reaction, and how much substrate do you need to give that enzyme in order to get it to, well, its Vmax or half of its Vmax. So those two numbers, your Km and your Vmax, will be useful to evaluate an enzyme. For instance, and I always like to think about this as kind of an extreme, um, or sorry, let me rephrase this. But whenever I think about Km, one of the other things that I think about is, well, I think about kind of this leads me in the direction of thinking about efficiency. Now, if we have an enzyme that has a Km for substrate 1, subs A, and subs B. So substrates A and substrates B. Um, we have an enzyme that has a Km of, I'll just use those same numbers, 0.1 millimolar and 0.01 nanomole, or sorry, that's not what I did, 0.1 nanomolar. Would everyone add to the chat, yes or no, thumbs up, whatever, um, add to the chat if you agree with the statement that you need more of substrate A um, to get your reaction to half of maximum velocity than substrate B. Okay. Now, with that in mind, if you think about it in terms of what do you need, is it more or less? Um, what do you think, or do you think that there's a correlation between Km and affinity? Kind of asking a leading question there, but absolutely. The lower the Km is, the greater your affinity, the greater your enzyme's affinity for a substrate is. So between these two, we've got substrate A and substrate B. Which does our enzyme prefer to bind to? Substrate A or B? Add it to the chat. Wonderful. Perfect. Oh, it's B. Don't worry. Don't worry. Okay. So our enzyme is going to prefer B because it needs less of it to get to half of its maximum velocity. That's a fantastic question to ask. We are going to, efficiency is kind of, when we talk about efficiency, we have to bring in another kinetic parameter. It's almost like, you know what, whenever you talk about significance, like if you go and you're talking to your cousin about, well, what's significant about this is blah, 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 blah. You can use the word significant very freely, but then it has a unique definition scientifically. So you have statistical significance. So the same thing sort of goes with respect to efficiency. So we can't necessarily say that a lower Km means a more efficient substrate. We'll bring another kinetic parameter in, but not until after this first module is completed, so that then we can evaluate an enzyme's efficiency. That's a great question, though, or that's a great observation. So when we go on, and we are looking at our Lineweaver-Burke plots, they're very valuable in the context of competitive inhibition. If you look at, I I have kind of a love-hate relationship with this graph right here because I feel like it always gives you it always deceives people. Because whenever I look at this, I can say, oh, okay, yeah, my Km, it changes. We've got our no inhibitor. We got our no inhibitor situation right here, and then plus inhibitor, and then double the inhibitor concentration. And I look at those intercepts, I'm like, okay, cool. Yeah, I get it. My Km changes. But then whenever I look at this, I also see my maximum velocity. And none of these aligns actually achieve the maximum velocity. Um, Truth be told, as these go on into infinity, all three of these lines will eventually reach the exact same place. The reason for that is our maximum velocity is not impacted in the presence of a competitive inhibitor. Only our Km is impacted by a competitive inhibitor. That's one of the reasons I think that this is the reason that I love this graph is because it shows that there's a shortcoming of the Michaelis-Menten plot. And it says that if you really want to evaluate an inhibitor, you need to look at the Lineweaver-Burke double reciprocal plot. I hate this plot though because it doesn't really show the full story. Um, at any rate, we're going to move on from here because we've talked about Km and Vmax and how they change with respect to a competitive inhibitor. Our competitive inhibitor, our Vmax, does not change at all. Our Km, however, it does. So, move on from there. To visualize a competitive inhibitor, I think that it's kind of the inhibitor that is like most palatable to sort of understand. Um, because what is it going to look like? It's going to look like the substrate. It's going to look like an enzyme's natural substrate. Alternative to that, it could look like what's known as a transition state analog. And a transition state is kind of like, well, while this reaction is being catalyzed, there's a particular place in time that a molecule looks like this. You know, a reaction has partially been completed. Um, and that is one way in which people will design an inhibitor is they'll say, okay, well, here's this transition state of this particular molecule as the reaction is carrying on. So we're going to design something that looks exactly like that and just kind of plugs in there. It matches up with this transition state version. Alternatively, they can be product analogs, or they can be they can be product analogs. Now, with that in mind, this is a nice little model of well, what one could look like. We have our natural substrate. Here's our enzyme. Enzyme binds to the substrate, completing this sucker right there. Then what's going to happen is our diamond ball shape is going to be broken, and we're going to release product one and product number two. Well, in the event that we have a competitive inhibitor, notice how it's got this triangle sort of structure. That's going to match up with the active site, in which case it's going to basically block your natural substrate from binding. So, okay, cool. It jumps in there, stops the reaction from happening, stops things from getting moving. So we have our free enzyme that never ultimately binds that substrate. And we form this Nelly EI structure, and we never form this ES structure. Now, there's a little bit more to it than that with respect to an enzyme's affinity for the inhibitor. But with a competitive inhibitor, one of the questions that I always like to ask is, in the presence of a competitive inhibitor, will ES be formed? Answer in the chat, yes or no. Will ES be formed in the presence of a competitive inhibitor? Sometimes you guys are kind of picking up some of the things I'm setting down. Yeah, to a smaller degree. Um, but yeah, it's much less likely in the presence of a competitive inhibitor. Great responses. Great job, everyone. Um, but if you have like a abundance and excess of that inhibitor, well, then chances are you're going to be shifting the equilibrium in one direction. Okay, now with that said, an example of a transition state analog, this structure right here, 1,6-dihydroinosine. This is a molecule that is a transition state analog for the enzyme adenosine deaminase. And so adenosine deaminase, what it's going to do is it's going to take adenosine and it's going to make inosine. This is a reaction in the process of in the metabolism of nucleic acids. And so this dihydroinosine, notice how it looks a lot like this structure right here, which is a transition state molecule. So in this reaction, going from adenosine to inosine, what I want you to notice is that we are ultimately removing this nitrogen or this NH2 in favor of this carbonyl oxygen. So that's what we're trying to do. And well, dihydroinosine, notice how it looks very similar to our transition state. The difference is that, yeah, they both have a hydroxyl group. They both have that alcohol up there, but our actual transition state, so our natural substrate, well, it still has that NH2, whereas our transition state analog in that place has a hydrogen. So it's kind of a bait and switch. It's like, hey, I look exactly like the transition state molecule. Not really. So it's all about deception and dishonesty. That's what inhibition is. And, saving lives and cancer therapies. But I am fine with being dishonest towards the abstract concept of cancer. And if you object to that, that's your prerogative, much like the Britney Spears song, My Prerogative. Okay, so that's what competitive inhibitors are going to do. We're going to look at those most often as a Lineweaver-Burke plot. Now, with respect to some of what they look like, well, yeah, sorry, this is just kind of belaboring the point that competitive inhibitors are typically going to look like your natural substrate or a transition state analog or a product. Now, next up, uncompetitive inhibitors. An uncompetitive inhibitor is going to have a different kind of pathway that we follow for kind of the formation and the different species that are formed. I'd like to draw your attention over here to the right-hand side of the screen. What we've got is our uncompetitive inhibition model. In an uncompetitive inhibitor, it is not going to be competing at all with the free enzyme. So an uncompetitive inhibitor sees the active site of the enzyme and says, don't care. I could care less. What the uncompetitive inhibitor is interested in is binding to this formed ES complex. Did you say competitive inhibition is more reserved for unnatural biochemical processes like you would see it in medicines? I believe that's what I've got on the previous slide. Is more reserved for unnatural biochemical process. I don't think that I ever actually said anything like that. In terms, I think that it's pretty common to try to develop a competitive inhibitor when you're thinking about like targeting a drug or developing a drug. I think that a competitive inhibitor is kind of the natural like process where you're going to be like, oh, okay, well, we know what the substrate looks like. We know the mechanism. So let's just try to design something that looks like one of those steps. Um, would you only see it in medicines? I don't think that's necessarily true. But sorry, that's just kind of broad for me to be, I guess, definitive. So yeah, that's what I got to say there. An uncompetitive inhibitor, well, what it's going to like to do is bind that ES complex. So it could care less about the free enzyme, but whenever the enzyme has bound to the substrate, then something about it makes it possible for that inhibitor to bind. So I always like to compare and contrast the competitive and uncompetitive structures because those two, if you look at our kind of schematic here, and if you remember what our competitive inhibitor looked like, it was E plus S yields ES yields E plus P, and then plus I yields EI. So those right there, I like to compare and contrast them because they kind of don't interfere with one another in these schematic ways. Um, there's they're kind of definitive from, or they're kind of segregated from one another in terms of what they do. Um, Now, what does this mean in terms of, I guess, kind of the design and the what you should expect? So when it comes to looking at an uncompetitive inhibitor and what to expect, what you're going to notice on a Lineweaver-Burke plot, so you're going to notice that the no inhibitor and then plus inhibitor, you're going to notice that the lines are parallel to one another. So with that to say, let me ask you a couple of questions. Does the Km change with an uncompetitive inhibitor? Yep, it sure does. Now, does the Vmax change? It does. Both your X and Y intercepts change. Now, if you notice those lines, they're all pretty parallel to one another. So I always kind of think about it as they change sort of hand in hand. Like if the Km goes up twofold, then the Vmax is going to go down twofold. So they kind of both change at a similar rate to one another. Now, with respect to what sort of questions might you see regarding this? Well, your questions are going to be, what are the species that can be formed? And whenever I say what species, I'm referencing ESI. So can EI form in the presence of an uncompetitive inhibitor? EI is not going to form in the presence of an uncompetitive inhibitor. This little schematic shows us that. What we're going to see is instead the enzyme and the substrate have no problem interacting with one another. Our enzyme will bind to our substrate, no issue. But then the question is, whenever we get to that ES complex, where do we go from there? Well, where we go is our free inhibitor then says, I'll bind. And so that's what's going to happen with an uncompetitive inhibitor. That's in contrast to our competitive inhibitor. And with our competitive inhibitor, we're not going to see that ESI complex form. We'll see ES form, but that's only if the enzyme binds to the natural substrate. Okay. Now, one of the things that I always like to ask and be thoughtful of is, okay, so this right here is no inhibitor. So I like to come up with little numbers. Let's say that this is -1. I'm going to go ahead and call this -2, -3, -4. Okay, so there's my x-axis values. Then up here, I'm going to go with, let's just go with 2, 3, 4. In the chat, answer this question. What is this A prime equals 2? That indicates that our concentration of our inhibitor is 2 millimolar, we'll say. Just 2x the concentration. And the x is just some arbitrary amount. With this A prime, or alpha prime, makes it sound like a sci-fi movie or book. A prime equals 2. What's our Km? And then, what is our Vmax? So we've got nice little numbers there. And then we're looking at this right here. This right here. Okay, so got my Vmax, my Km, and my Vmax. A prime or alpha prime equals 2. So I'm looking just at this line, this top line. So my Km is going to be set that -4 equals to -1 over Km. And then I'm going to say Km 0.25. Then for my next one, well, my number is effectively the same. My 4 equals 1 over Vmax. So I think that um, this this number right here, that 2 that I just circled, we kind of don't need to worry about that. And what I mean is, or the reason that we don't need to worry about that is because that number is useful for telling us the inhibitor concentration that was used for the trials that generated this line right here. When it comes to solving for our Km or our Vmax, this is a double reciprocal plot. So all that we needed was the X and Y intercepts. So our Km and our Vmax are both 0.25. And that 0.25 is just because I kind of arbitrarily decided it was 4 as my intercept. So this number right here is 4. This number right here is -4. Does anyone follow that? Okay. So now let's go ahead and solve for. Okay. Okay, thank you. So I'm going to go back just because this is I'll use these numbers. Erase all this. Okay. So we've got 2 lines. And I'll draw the Michaelis-Menten plot that corresponds to this. So this bold line is our enzyme catalyzed reaction with no inhibitor. Because what we always want to do when we're evaluating an inhibitor is we want to know the answer to the question of, does it do anything? Does this compound, does this molecule that somebody designed, somebody synthesized, an organic chemist synthesized, and they said, hey, what this molecule is going to do is it's going to stop this reaction. Here is our organic molecule, and we're going to throw it in with our mixture, and we're going to see if it works. Now, in order to see if that molecule does anything, we have to get a baseline. And so that's what this bold line is showing us. That's our baseline where we can figure out our Km and our Vmax. And so the first thing that I'm going to do is I'm going to look at this number right here, my y-intercept. So my y-intercept, I'll say y-intercept for no inhibitor. That number, somebody tell me what they think that number is. I've got 0.002 and then slightly above that. I like it. We're going to go with 0.00 or 0.0023. Can I get a thumbs up or a yes if they follow? And that's good. Okay. So we decided what that number is. And with that number, what can we do? We can figure out our Vmax without our inhibitor. So this is like your enzyme is optimally set up to do its reaction. What is our Vmax? Vmax is equal to, well, I'm going to go ahead and draw a little line because what I like to do is I like to say y-intercept is equal to 1 over my Vmax. I just solved for my y-intercept. I said that was, and I'm going to come over on the right-hand side of the screen, 0.0023 equals 1 over Vmax. Does everyone follow what I did there? Okay. So now I'm going to use my computer phone, and I'm going to say 1 divided by 0.0023. And I'm going to erase all this, and I'm going to give myself my new Vmax. My Vmax is 434.8. Did anyone get something similar to that? Okay, cool. Now our hypothetical units for that. Well, what give me some units for a velocity for an enzyme catalyzed reaction. We've got to have two variables. Just like miles per hour, we've got to have a time interval. And then what else do we have to have? We're measuring product generation, right? So how about nanomolar per second? Oh, I like it. Kristen. Okay, perfect. Okay, so we've got our rate, our maximum velocity, and then the next thing that we've got to do is come up with our Km. Well, our Km, our x-intercept. Oh, rats, Joel. Okay, I got to I got to extrapolate out this line here. I'm going to say that this is about negative 0.6. This line. I'm going to come back to this dashed line in just a second. Um, just between the 71 of us, I'm going to be lazy. You know what? I'm not going to like a third decimal place. I'm calling this negative 0.5. Does that sound good for everyone? Okay. My x-intercept is negative 0.5. This is x-intercept is equal to negative 0.5. My km, how do I solve my km? On a double reciprocal plot, I have, well, x-intercept is equal to, and this is a negative x-intercept, is equal to negative 1 over km. Does everyone follow that? Because that's what that graph tells us. So now I'm going to take my x-intercept, it's negative 0.5, and plug it in down here. And you might think, oh man, he's really using that negative a lot. I am. And the reason for that is because what people will do is they'll take that negative 0.5 and they'll see this and they'll be like, oh, I'm going to drop the negative. I'm going to put that in. And then they end up with a km that is a negative value. If you feel comfortable just dropping it right here and saying 0.5 is equal to 1 over km, by all means, do that. You just have to keep that value straightened out so that you can be good with that. So now, again, pat myself on the back for the lazy numbers here. Km, 1 over 0.5. I'm going to go with a Km equal to 1 divided by 0.5. Ooh, 2. I like that. Okay. So I now have my kinetic parameters for my enzyme in the absence of an inhibitor. So it's almost like this other dashed line, the black dashed line, isn't a part of what we're thinking quite yet. So this is the baseline. Someone's done these experiments and they came up with a plot that looks, here's our trial, boom, 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 boom. Okay, and then this is just the Michaelis-Menten plot. Came up with, here is our Km right here, Vmax divided by 2. If Km is half of Vmax, why can't you just divide the Vmax we got by 2? Because then you're dividing the Vmax and you're not solving for the concentration. I'm happy that you asked that because that was a younger Joel Gray's understanding of Vmax and Km. And lo and behold, every time I got that question wrong on a test, I said, they must have graded it wrong. As opposed to me just being wrong every single time. Okay, so now we have no inhibitor and basically our values. And not like our personal values held close to our heart or anything like that, but just instead our numbers. So now what we need to do is someone has gone about and they have done these trials, but they've added the inhibitor. Now, when we were doing all of our trials or doing enzyme catalyzed reactions, what did we do from trial 1 to trial 2 to trial 3 with our enzyme concentration? How did our enzyme concentration change from every subsequent trial? Give you a hint. It starts with a C and ends with an onstant. Stayed the same. We keep it constant. You're absolutely right. We keep our enzyme concentration constant, and every successive trial, our substrate concentration, we increase that, which is why if you look at our x-axis here, this is our substrate concentration. So we increase our substrate concentration. Now, we've got basically two options. We can either, when it comes to introducing an inhibitor, you can either keep the enzyme, or keep the inhibitor concentration constant, or you can vary it. Now, raise your hand if you love multivariable calculus. Or let me rephrase that. If you like multivariable anything, when you introduce a new variable, you are making it more complicated. So, what do you think we should do whenever we're testing the efficiency or testing the impact that an inhibitor has? If you think that we should, let's say, if you think that we should change it for every successive trial, I want you to unmute yourself and say, I do. I'll wait. You're right. Good job, everybody. Exactly. No, we do not want to change our inhibitor because if we do that, then what are we going to do? We're going to double it. We're going to triple it every single trial. We do not want to do that. So instead, when you see something like this plus inhibitor, this would be inhibitor concentration. I'm just going to put this in brackets, is fixed. So what that means is you would say, okay, well, I'm going to add 2 nanomolar of an inhibitor. Do I know if that inhibitor is going to have any sort of impact? I don't. That's why you would do it at 2 and 4 and 6 and 8. And you would keep titrating it. You would do basically you'd do like 10, 15 trials, and then you'd have 50 different tests of the inhibitor and how much of it you needed to add. So our inhibitor concentration, when we see this dashed line, that reflects a bunch of trials where the inhibitor concentration is the exact same. The only thing that changes is our substrate concentration. Okay, now what we want to do is we want to figure out, well, how much did this inhibitor impact our results? And in order to do that, I have to stand up. And I have a standing desk, and it is raising up. Not that I have really amazing leg strength where I can make those adjustments very easily like that. Okay, so when I'm looking at this plot and I'm looking for how did my inhibitor impact my results? I've got my results of my Km and my Vmax in the absence of an inhibitor. Now I have my dashed line that shows me, well, what is my Km and my Vmax plus inhibitor. Now, what I'm going to do is I'm going to give us a nice number right here. I'm going to call that negative 0.8 is my x-intercept. And what I want you guys to do is I want somebody to give me a y-intercept in the plus inhibitor. Give me my y-intercept. I like it. 0.0033. Looks like an 8 because I'm not good at writing. 0.0033. Nice. Okay. I'm going to dispatch you guys. Come back to me with a KM and a Vmax. I'm going to do the same thing. Okay, we got some responses rolling in. And what I'm seeing, see a Vmax of about 303 and a Km 1.25. Okay, now what does that mean for each one of our numbers? Okay, our Km, and I'll just call this millimolar. Millimolar, I'll give some units there. My Vmax, do I have the same units? Yeah, nm per second. Okay, what happened to my Vmax in the presence of my inhibitor? Did it go up? Did it go down? Did it say this? Mackenzie, you're absolutely right. It decreased. My Vmax went down. So that means our enzyme, in the presence of this inhibitor, this enzyme slowed down the reaction. Good? Yeah, seemingly. Okay. Now, my Km. What happens to my Km here? My Km went from 2 millimolar to 1.25. Okay. Yes. Yes. My Km, the measure of my affinity, my Km, the number Km decreased. So that means my enzyme's affinity for the substrate for the substrate increased. It's very important that you keep that straight. So I will ask you, how did the Km change? Did the Km change? How did the affinity change? This inhibitor, this model, causes reaction to slow. Would everyone agree with that statement? Give me a thumbs up or a yeah in the chat, or an emoticon. Okay. It causes it to slow down. But then this is kind of a tricky part. Nice sunglasses emoji. I like it. Our enzyme's affinity for our substrate went up. That always seems like that's tough for me to wrap my mind around because personally, whenever I hear about affinity going up, that to me sounds like a positive thing. And one thing that I caution you against is being like, oh, well, this is good or this is bad. That's not the question. Don't look at this as this is positive because then you're kind of projecting morality on it. And that this isn't a philosophy class. You're kind of projecting like a value to it. Don't do that. Now, how does it make sense in a mechanistic standpoint? Well, one of the ways that it always makes sense, or it's helpful for me to make sense, is you have this enzyme that what it's capable of doing is binding the substrate and producing a product. One round. One enzyme will pick up a substrate, produce a product. And then what will it do? It will go back, pick up another substrate, produce a product. It will continuously do that. Now, let's say hypothetically, okay, before I do, so the inhibitor is toxic for the enzyme. Not necessarily toxic. Um, the inhibitor is interacting with the enzyme. So it's binding to the enzyme. It's binding to the enzyme substrate complex. Um, Toxicity, again, that's a term that has a physiological impact and physiological relevance in terminology. So just be cautious with terms like that. Now, what we've got here is our enzyme. Let's say that you have 100 copies of the enzyme. I mean that it doesn't let the enzyme do its job. Okay, it's all relative. It speeds up. The enzyme is going to speed up the reaction, but we're not looking at compared to the uncatalyzed reaction. We're looking at how does this inhibitor adjust, slow down, or not at all the reaction in the absence of an inhibitor. So we are looking at this. We're with an uncompetitive inhibitor, and with any inhibitor, We're asking, how does this inhibitor impact this right here? Well, an uncompetitive inhibitor siphons off this ES and makes this ESI complex. So what it's doing is siphoning that off. Now, imagine if we have 100 copies of the free enzyme. It's going to buy the substrate. And let's say that it makes 100 copies of this ES complex. 100 of them. Let's say that the inhibitor is present. What it's going to do is it's going to bind to, let's say, 20 of them. And we're going to get 20 ESI. When we get those 20 ESI, what's going to happen to the remaining 80 ES complexes? What are they going to do? They're going to make a product. No problem there. They're going to make that product. Okay, so then we're going to have 80 free enzymes because we're going to generate 80 products. What's going to happen to those 80 free enzymes? Back to the beginning. They're going to catalyze the reaction again. But what about the other 20? Well, they are secluded as this ESI complex. They're basically kind of compartmentalized off. They are not going to be able to catalyze that reaction again. So what an uncompetitive inhibitor does is it kind of dilutes your enzyme concentration, which is why our affinity for which is why our Km goes down and our affinity for the substrate seemingly goes up. Okay, so the calculations that we just did here, where we took a graph, a double reciprocal plot, calculated our Km and our Vmax, and we kind of interpreted that, those are all things that I want you to be able to do. In addition to that, I want you to understand that an uncompetitive inhibitor, and I think that this is a good exercise to do where you look at it and you say, okay, well, what did the uncompetitive inhibitor do to the Vmax? It drove it down. What did it do to the Km? It drove it down. What are the implications of that? Well, the Vmax, or the rate that the product is being generated, well, it went down. The affinity that our enzyme has for our substrate, ooh, that went up because Km is a measure also of affinity. Now, I'm going to move over to a mixed inhibitor. So we've got a competitive inhibitor and an uncompetitive inhibitor so far. A competitive inhibitor goes to the active site. An uncompetitive inhibitor avoids the active site and goes to another part of the protein or another part of the enzyme where but only when the natural substrate is already bound. So when you look at E versus ES, what does an uncompetitive inhibitor want to do? Boom. What does a competitive inhibitor want to do? Well, it wants to ignore ES and instead go to free E. So between a competitive and an uncompetitive inhibitor, I think that it's helpful to think about the potential species that are formed. EI, ES, ESI, and so on. Now, we have two more examples of types of inhibitors. We have a mixed inhibitor. Now, a mixed inhibitor, what it is going to do is it is going to be capable of binding either the free enzyme or the enzyme substrate complex. So with a mixed inhibitor, you can form EI. You could also form ESI. Now, the question is, well, what's it doing? What is it actually doing? And the way that you answer that question is by looking at a Lineweaver-Burke double reciprocal plot. So with a Lineweaver-Burke double reciprocal plot, again, we've got our solid line to indicate that there is no inhibitor present. So no I. And then we've got our dashed line to indicate plus an inhibitor. An inhibitor is present. Now, what do you notice about the Vmax? Not necessarily one way or another, but Does it remain the same or does it change in the presence of a mixed inhibitor? Add it to the chat. It changes. Okay. Same thing goes for the Km. Does the Km change or does it remain the same? Okay. Seeing that it changes. Now, let's look at, and this is the tricky thing, or this is one tricky thing about this, is how does my Km change? Not my x-intercept, but my actual Km. Does my Km go up or does it go down? And the way that I think is helpful to answer this question is to assign a particular value. In the absence of the inhibitor, I'm going to call this negative 0.5. In the presence of my inhibitor, I'm going to do the calculation to figure out my Km in the absence of the inhibitor. I want you guys to do the Km calculation for in the presence of the inhibitor. So I want you to use that negative 0.5 or that negative 0.4. So my Km, and we'll just report to the chat whenever we get them. So I got 2, Kristen got 2.5. So what did my inhibitor do to my Km? What's the difference between 2 and 2.5? My Km went up. So the mixed inhibitor, my Km went up. What does that mean for my enzyme's affinity for my substrate? Lower affinity. So I just got a question for, can I show the individual steps for how I solved it? I absolutely can. So my x-intercept is equal to negative 0.5. My x-intercept is equal to negative 1 over Km. So I'm going to say my x-intercept is negative 0.5. Now I'm going to say negative 0.5 is equal to negative 1 over Km. Now what I'm going to do is I'm going to do the algebraic rearrangement. I like to say the word algebraic. These negatives are going to cancel out. So Km is equal to 1 over 0.5. 1 over 0.5, Km, is equal to 2. So that is my Km in the absence of my inhibitor. In the presence of my inhibitor, same thing. Negative 0.4 is equal to negative 1 over Km. And therefore, my Km is 2.5. The same thing for, I would do the same thing for my Vmax. Well, this would be 0.0024 or something like that. And then that y-intercept is going to go up. Those are reciprocal values. If we jump back, I think that it's helpful to look at these values right here. When my y-intercept when the value of my y-intercept increases, what does that mean for my Vmax? That means my Vmax decreases. So here, what we have is this causes Km goes up. Vmax goes down. Okay? So this is what a mixed inhibitor is going to do. The important thing about processing what a mixed inhibitor does is to see this right here. All of the possible ways that a mixed inhibitor can bind, but then also looking at a graph. So one of the questions that I will ask you or give you on an exam would be something where I'd show you a graph like what's circled right here and say, this pattern represents which type of inhibitor. This is a mixed, competitive, non-competitive, uncompetitive, and so on. Okay, so being able to look at that and piece it together and saying, okay, well, that's the mixed inhibitor. One of the ways that I think about this is, do my lines intersect? They do. where do they intersect? I always think back to this is quadrant 1, quadrant 2, quadrant 3, this is quadrant 4. Where is my intersection of my lines taking place? It's in quadrant 2. So whenever I think about a mixed inhibitor, I think quadrant 2. That helps me out because then I can kind of say, okay, well, that's where my lines are going to intersect. That is a mixed inhibitor. Now, I'm going to go on to my next inhibitor in the interest. Yeah, good. My next inhibitor is a non-competitive inhibitor. A non-competitive inhibitor, oh snap, it looks the same. Oh man. Well, yes, yes, yes. Multiple people I know probably did the exact same thing that one of your classmates did, and that was a move back from your computer. Fair. The best way I think to understand the differences in these types of inhibitors is to look at the plots. When you look at the plots, then you can kind of narrow it down and say, all right, well, where do my lines intersect? Okay. So for a non-competitive inhibitor, again, quadrant 1, 2, 3, and quadrant 4. Good thing is we don't really have to worry about quadrant 4. Where do those two lines intersect for a non-competitive inhibitor? At the interface of quadrants 2 and 3. Now, what does that mean? What that means is you can, sorry, that sounded like I was getting snarkier and rude. That means you can plug this number in and solve it for yourself. That's not what I was intending to do. Instead, what I'm getting at is when you see this intersection and you see those two lines intersect, you can say something like, okay, well, the x-intercept for my plus inhibitor or no inhibitor, it's going to be the same. Therefore, my Km is not changing in a non-competitive inhibitor. The next thing that you can do is you can look at, okay, well, here's my Vmax with no inhibitor. And then here is my plus a non-competitive inhibitor. And you can solve for those values. And you can see, okay, well, this number, this y-intercept value increases in the presence of a non-competitive inhibitor, which means that my Vmax decreases. Now, I'm not intending to rush through this, but what I want to do on the next slide is show you all of the different graphs. Okay. Now, my recommendation for how to distinguish these graphs from one another is as follows. This one is by itself. Which graph is this? This is an uncompetitive. Uncompetitive inhibitor. Don't worry about that. Sorry. Think about that as, okay, well, I don't really want to compare that graph to my other graphs. And the reason for that is for all of my different lines there, my trials with no inhibitor, and then my other trials with the inhibitor, where I've increased my inhibitor concentration. Those lines never intersect. So no intersection. So no intersection between those different lines. That leaves me with 3 other graphs. My question for you, and answer this, the lines don't cross each other, so they... Sure. That's a great summary. With my other 3 graphs, does my line depicting the data for my no inhibitor and my lines depicting plus an inhibitor, do those intersect? They do. When you look at those different lines, what I want you to recognize is their differences from one another. One of them is on the y-axis. Another one is on the x-axis. And then the last one is in quadrant 2. Does everyone follow that right there? So we have 4 graphs, but they are kind of separate from one another and distinct from one another. I think that's the best approach to take with this. So then we can jump back and say, all right, well, non-competitive, that is on our x-axis. So I'm just going to label that as NC. So my x-axis is non-competitive. And whenever I think about that, I always try to think of like an analogy or some sort of fun mnemonic or metaphor or something like that. And let's see. Whenever I think of NC, I think of the state of North Carolina. And let's say that's a competitive state. I don't know. It's sometimes a battleground state in presidential elections, sometimes. Then we've got our y-axis. This is our competitive. So we've got our competitive, our uncompetitive, our non-competitive, and then last but not least is our mixed inhibitor. Those 4 different graphs, we have intersection, we have no intersection, which is indicative of an uncompetitive inhibitor. Then we have intersection on the y-axis, which is our competitive inhibitor. Then we have intersection on the x-axis, which is non-competitive. And we've got intersection in quadrant number 2, which is our mixed inhibitor. I think that is the best way to do it and build out from there. Because then you can draw those little lines and make approximations. And you will have a question, or you will have questions on your exam that just show you the graph and say, what type of inhibitor is this? Now, with that in mind, I've got one last poll question, and I'm going to share it right now. So an inhibitor is designed to prevent binding of the natural substrate. After doing some experiments with this inhibitor, you notice that the Km does not change, but the Vmax does. Based on this, which of the statements below is your best explanation? We've got, it is not competitive. In a competitive inhibitor, the Km and Vmax change. It is not competitive in a competitive inhibitor, the Km and Vmax do not change. And then it is not competitive in a competitive inhibitor, the Km will change and the Vmax will remain the same. So there's kind of a couple of different layers to this question. One of those layers is that a molecule, here my prompt is a inhibitor is designed to prevent. So you might be working in an organic synthesis lab and you're like, oh, I know what the natural substrate looks like. I know what transition state looks like. Here's the molecule that I've produced. Does that mean that it is a competitive inhibitor? No. You might design it to do one specific thing and expect that it's going to, but when you actually use it, you might see a different result. And what I mean by that is it still might be a functional inhibitor, but it might not be functioning in the way that you expect. Okay, we've covered a lot today. The answer that I was going for this one, I'm going to share the results. It is not competitive. In a competitive inhibitor, the Km will change and the Vmax will remain the same. Because with a competitive inhibitor, what we see is the y-intercept remains the same in the absence and in the presence of an inhibitor. I'm going to go ahead and stop my recording.